Pluto was once thought to be a planet in our solar system. It remains a dwarf planet that captivates and eludes explanation. Situated far from Earth, despite its previous classification, recent bold assertions by esteemed astrophysicists Michio Kaku and Neil deGrasse Tyson have stirred new interest in Pluto. They have suggested that Pluto's frozen world could be heading in the direction of a devastating encounter with Neptune, triggering a flurry of inquiries regarding the consequences and plausibility of such an event. Could this scenario be a theory that is exaggerated, or is there a proper cause for concern? Let's investigate the potential consequences of a Pluto-Neptune collision. Pluto was classified as a planet, but due to being reclassified as a dwarf planet and its erratic orbit, this choice has kept it a topic of ongoing discussion in the world of astronomy. The most recent leading scientific studies suggest that Pluto's orbital course poses a danger. It intersects with Neptune's, raising alarms concerning the possibility of a fatal impact. Because of their proximity in respective orbits, can a collision between Pluto and Neptune actually occur? And if so, what would the implications be? Pluto's journey around the Sun is unlike that of any other planet in our solar system. Its orbit spans a complex 248 years, indicating that Pluto, discovered in 1930, hasn't even completed one full orbit yet. But the unusual nature of Pluto's orbit doesn't end there. It continues with a deviating elliptical path, significantly different from the near-circular orbits of most other planets. To complicate matters further, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its inclination much steeper than that of other planetary routes. The fascinating aspect of Pluto's orbit is its relationship with Neptune's. For about 20 years during each of Pluto's prolonged orbits, it gets closer to the Sun than Neptune, an odd coincidence that raises an important question. Why haven't Pluto and Neptune collided yet? The powerful gravitational forces from other celestial bodies hold the answer. After Pluto was discovered, astronomers quickly acknowledged the erratic nature of its orbit. Unlike the nearly flat orbits of the other planets, Pluto's steep angles and elliptical trajectory were starkly different. The complexity of its path became even more apparent as scientists realized that Pluto's orbit crosses Neptune's. Despite these unconventional aspects, Pluto's orbit has remained surprisingly stable. This is due to gravitational effects from other planets, especially the influence of what's known as the three-body problem in celestial mechanics. This theory seeks to explain the interactions and movements of three celestial bodies, such as Pluto, Neptune, and the Sun. Pluto's motion through space can be erratic, as even minor modifications to its initial conditions can cause dramatic changes in its long-term trajectory. Yet simulations have demonstrated that Pluto's orbit has remained stable over long timescales, despite how chaotic it may appear at first. The significant gravitational pull from massive bodies like Jupiter plays a crucial role in stabilizing Pluto's orbit. These forces, acting over billions of years, are necessary for preserving the overall order of our solar system and preventing catastrophic disruptions. Pluto's orbit demonstrates a fascinating balance of stability and chaos. It's important to acknowledge the inherent difficulties in predicting the movements of celestial bodies, especially those with irregular orbits. While numerical simulations can provide valuable insights, they also emphasize space's unpredictable nature, making long-term predictions uncertain. The issue brought up by astrophysicists like Tyson and Kaku about a potential collision between Pluto and Neptune may seem far-fetched. However, their cautions have caught the public's attention. If such a collision were to occur, the consequences could be detrimental to our solar system. The impact would release a great deal of energy, most likely leading to Pluto's destruction due to its small size and icy composition. The resulting debris could be dangerous to nearby planets and their moons, including Earth. The effects of a Pluto-Neptune collision would not be limited to Pluto alone. The collision could alter Neptune's orbit and atmosphere, depending on the nature of the incident. According to Michio Kaku, a renowned theoretical physicist, this scenario provides a unique perspective on space. His extensive study of string theory and celestial mechanics suggests that understanding Pluto's orbit could lead to useful insights into the physics governing space exploration. By examining gravitational interactions through Pluto's orbit, we can acquire valuable information for future space missions. This knowledge could help scientists better prepare for potential space threats and contribute to the exploration of distant areas of the solar system. Moreover, principles derived from Pluto's orbit have broader implications for research into other dwarf planets and trans-Neptunian objects. Pluto's complex orbit challenges our comprehension of planetary motion, showing us how dynamic and unpredictable celestial movement can be. The connection between celestial mechanics and string theory emphasizes the importance of understanding how planets and other bodies interact. In the event of a collision between Pluto and Neptune, it would be a landmark event in cosmology. Such an occurrence would offer a rare opportunity to explore string theories under extreme conditions. This collision would release a vast amount of energy and potentially offer a glimpse into the behavior of elementary particles at high energy levels, the main focus of string theory. Despite the likelihood that a direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications would be profound. A collision of this kind would provide fresh opportunities to explore the universe's fundamental nature, especially in fields related to string theory and theoretical physics. Pluto continues to capture the imagination of astronomers and space enthusiasts alike. The ongoing debate over its status as a dwarf planet has reinvigorated interest in its role in the solar system. The concerns raised by Tyson and Kaku underscore the complex forces that govern celestial movement, highlighting the importance of understanding orbital and gravitational mechanics. These forces are vital to comprehending the dynamics of our solar system and the debate surrounding Pluto's classification. Pluto's elliptical orbit and steep inclination defy conventional theories of planetary motion. Unlike the near-circular paths of neighboring planets, Pluto's orbit crosses Neptune's at certain points during its extended trip around the Sun. The gravitational forces produced by Neptune and other planets have played a critical role in maintaining Pluto's stability over centuries. Despite this, predicting the future actions of celestial bodies remains a complicated and uncertain task. The possibility of a collision between Pluto and Neptune serves as a reminder of the inherent unpredictability of planetary dynamics. Though such an event seems highly unlikely in the near future, the gravitational interactions between Pluto, Neptune, and other bodies illustrate the delicate balance that exists in our solar system. The study of Pluto offers crucial lessons for upcoming space missions. It aids scientists in exploring other distant celestial bodies and in gaining a. As our understanding of the cosmos grows, Pluto remains a symbol of how scientific discovery is an ever-evolving process. It reminds us that the universe is not static, it shifts, surprises, and forces us to rethink our most foundational ideas. From once being celebrated as the ninth planet to being reclassified as a dwarf planet, Pluto's story reflects the broader narrative of astronomy, a field driven by curiosity, data, and the willingness to revise old models in light of new evidence. The peculiar dance between Pluto and Neptune, marked by a 3:2 orbital resonance, meaning Pluto orbits the Sun twice for every 3 Neptune orbits, is one of the most intriguing natural mechanisms in our solar system. This resonance ensures that despite their intersecting paths, the two bodies are never at the same point at the same time. It's a cosmic safeguard that has likely prevented any catastrophic encounters for millions of years. Still, questions remain. What if this balance is somehow disrupted? Could gravitational disturbances from other celestial events, such as the passage of a rogue planet or a dense asteroid belt shift, impact this resonance? While simulations show the resonance to be stable over extremely long timescales, no model can account for every possible external factor in the cosmos. Astrophysicists argue that studying these edge cases, however unlikely, is essential. Not because a Pluto-Neptune collision is expected, but because the exercise strengthens our understanding of orbital mechanics, gravitational influences, and the fragile harmony that allows our solar system to function as it does. Beyond theoretical concerns, Pluto's place in popular culture and science education is also worth noting. The debate surrounding its planetary status has sparked global interest in astronomy, particularly among younger generations. It serves as a gateway into broader discussions about how we define planets, how science evolves, and how much there is left to learn. New missions targeting the outer solar system are already in conceptual stages. Scientists and engineers envision probes capable of exploring the Kuiper Belt, where Pluto resides, and gathering data from other dwarf planets and icy bodies. These missions, building on the legacy of New Horizons, could reveal more about the origins of our solar system, the nature of planetary formation, and perhaps even the early conditions necessary for life. In essence, Pluto is more than just a dwarf planet. It's a scientific enigma, a cultural icon, and a crucial puzzle piece in our understanding of the cosmos. The questions it raises, about planetary motion, stability, and the influence of celestial mechanics, drive us to explore further, ask deeper questions, and look beyond what we currently know. As we stand on the threshold of new frontiers in space exploration, Pluto continues to remind us of the beauty and complexity of the universe, and of how much we still have yet to discover. Increase our understanding of the formation and the growth of planet systems. The discovery of Pluto and ongoing research have substantially contributed to our comprehension of the motion of the planets and the development of a region known as the Kuiper Belt, beyond Neptune, filled with small icy bodies. Understanding Pluto's orbit provides valuable clues about the gravitational interactions that may have shaped the early offering of the solar system, essential data for the future of space missions focused on exploring outside of potentially habitable worlds in our solar system. Although the likelihood of a Pluto-Neptune collision remains extremely low, the study of these objects from outer space serves as a reminder of the ever-changing nature of the universe. As we continue to explore the farthest parts of our solar system and beyond, the study of planetary orbits and celestial mechanics will remain important to our efforts to explore. The unique orbit of Pluto provides useful lessons on the difficulties of planetary motion and the forces that shape celestial bodies over time. The continued exploration of Pluto's orbit and its interactions with Neptune serves as a reminder of the erratic nature of the universe. As new discoveries are made and theoretical models are developed, we enhance our comprehension of the universe and advance insights into distant mysteries. Pluto's orbit not only provides answers about this distant world but also helps us predict future trends in celestial behavior, contributing to a better understanding of the forces that govern our solar system and beyond. In conclusion, the possibility of a Pluto-Neptune collision, though highly unlikely, emphasizes the fluid nature of the universe. Pluto's orbital research, encounters with Neptune, and the underlying gravitational forces provide valuable insights into celestial mechanics. As we continue to investigate these far-off bodies, we refine our models of planetary systems and enhance our ability to predict future cosmic events. The potential for discovery in this field is unlimited, and with technological advancements, so too will our ability to study and comprehend the vast and ever-evolving universe. The study of Pluto's orbit and its role in the solar system will continue to help us better understand the universe for years to come. Pluto's orbital behavior, with its unique interactions with Neptune, has long been a subject of fascination and intrigue. Despite this, within the scientific community, Pluto has been classified as a dwarf planet. It continues to challenge our comprehension of planetary dynamics. Pluto's orbit intersects Neptune's at several points without resulting in a collision, demonstrating the complexity of our Sun's gravitational mechanics. One of the most fascinating aspects of Pluto's orbit is its resonance with Neptune. This resonance, referred to as a 3:2 orbital resonance, means that for every 3 times Pluto completes its orbit around the Sun, Neptune completes 2. This synchronized relationship guarantees the two bodies never come too close to one another, despite their crossing paths. In this resonance, Pluto and Neptune are essentially locked in a cosmic dance, where their orbits are set in such a way that they never collide. This unique gravitational relationship is an excellent example of the precision and balance that exists in celestial mechanics. The forces exerted by Pluto's gravity and that of Neptune work together to maintain a stable orbit for both. Without this resonance, a disruption in Pluto's orbit could have occurred, possibly resulting in a collision or significant changes in its trajectory. Appreciating this, astronomers rely heavily on such interactions because they shed light on how celestial bodies maintain equilibrium, even when their paths appear jumbled at first glance. Moreover, the Kuiper Belt, a region beyond Neptune, is a treasure trove of icy bodies and dwarf planets. Pluto is the largest presently known object in this belt, and its orbit provides important data about the conditions that prevail in this faraway region of the solar system. The Kuiper Belt objects, KBOs, and TNOs, trans-Neptunian objects, are remnants from the beginning of the solar system, and their study allows us to peek into the conditions that existed during the formation of the solar system billions of years ago. Space agencies like NASA are now directing missions towards studying these distant regions. NASA's New Horizons mission, which flew by Pluto in 2015, offered us a new level of data and images of Pluto's surface and atmosphere. The findings from this mission revealed frozen nitrogen plains, complex ice mountains, and towering weather systems, suggesting Pluto is a geologically active world. The mission also showcased the diversity of the dwarf planet's moons, providing clues about how moons form and evolve in the outer solar system. The New Horizons mission also illustrated the growing capabilities of modern space exploration. These missions not only broaden our understanding of distant Pluto-like celestial objects, but they also open the door to greater ambitions, explorations into the Kuiper Belt and beyond. The success of this mission has sparked renewed interest in exploring these far-flung regions and could inspire others to pursue similar goals. Despite the apparent stability of Pluto's orbit, its tilted and eccentric trajectory raises concerns regarding the long run. The fact that Pluto's orbit is so different from the nearly circular orbits of the 8 major planets offers astronomers an engrossing puzzle. The inclined and elliptical nature of Pluto's orbit serves as a reminder that our solar system is not as orderly as it might seem at first glance. The chaotic behavior exhibited by Pluto's orbit could have profound implications for our understanding of planetary formation and evolution. It implies that planetary systems, especially those at the edges, might develop in unpredictable ways that were not considered before. If Pluto's orbit were to experience any major disruptions, it could have ripple effects throughout the solar system, potentially affecting the orbits of other objects in the Kuiper belt or even the planets themselves. Some scientists speculate that Pluto's interaction with other gravitational bodies, like Neptune, could provide insight into the early solar system's evolution. As scientists continue to study Pluto's orbit, they hope to uncover more information about the processes that shape the solar system and the role of gravitational forces in determining the orbits of planets, moons, and smaller bodies. These investigations are more than just intellectual pursuits, they carry practical implications for future exploration and space travel. Understanding orbital dynamics is crucial for mission planning, satellite placement, and potential colonization of other celestial bodies. Pluto, despite its distant location and dwarf planet status, provides a rich case study for such research. As astronomers and planetary scientists probe deeper into the behavior of Pluto and its neighbors in the Kuiper belt, they continue to find anomalies and exceptions that challenge existing models. For instance, Pluto's moon system, particularly Charon, presents a unique binary relationship that further complicates and enriches our understanding of gravitational interactions. The mutual orbit between Pluto and Charon suggests a shared barycenter that lies outside of either body, a phenomenon not commonly observed in other planetary systems. This peculiar configuration raises questions about how such a system formed and remained stable over billions of years. Could similar systems exist elsewhere in our galaxy? Might such relationships be more common than we previously assumed? These questions push the boundaries of our planetary science and cosmological assumptions. Additionally, the surface features revealed by New Horizons have inspired new theories about Pluto's internal structure and thermal history. Some scientists now speculate that Pluto may harbor a subsurface ocean beneath its icy crust, a finding that would significantly alter our understanding of where liquid water might exist in the solar system and where life might theoretically arise. The study of Pluto, once seen as a distant and relatively unremarkable outlier, has become a frontier in redefining what we know about the outer solar system. As technology improves and deep space missions become more sophisticated, our ability to study these remote objects will grow. We may even develop telescopes and instruments sensitive enough to detect interactions within the Kuiper belt in real time, offering unprecedented insights. In the broader context, Pluto's case serves as a metaphor for the scientific process itself. What begins as an assumption can be overturned by observation, what seems peripheral can become central, and what appears stable can reveal deep complexity upon closer examination. Ultimately, the journey to understand Pluto is part of humanity's larger quest to grasp the cosmos and our place within it. With each mission, each discovery, and each refined model, we take one step closer to unlocking the secrets of the universe.